Let's take a deep dive into a topic that is crucial for any kind of data analysis: the limitations of one-dimensional statistical values. The slide you see here illustrates this beautifully with what's known as Anscombe's quartet. Anscombe's quartet is a famous example from statistics, named after the statistician Francis Anscombe, who first published it in 1973. What you see on the left are four seemingly different scatter plots. Each plot shows a set of data points, the orange dots, along with a fitted linear regression line. At first glance, they look like four different cases, right? Well, visually, they certainly are. But here's the twist. If we calculate simple summary statistics for these four data sets, we get exactly the same values. On the right side of the slide, you see these numbers. The mean of x is 9 for all four data sets. The variance of x is 11. The mean of y is 7.5. The variance of y is 4.12. The correlation between x and y is 0.816. And if we run a simple linear regression, we get the same equation every time. Y equals 3 plus 0.5x. If you only look at these statistical values without visualizing the data, you'd assume that all four datasets behave in the same way. And that's exactly where the danger lies. Let's go through each graph slowly. The first graph shows a fairly typical linear relationship. The data points are scattered around the regression line with no obvious anomalies. The second graph, however, reveals a clear, non-linear relationship. There's a curve in the data, but the regression line doesn't capture this at all. Yet, it gives you the same statistical summary as the first graph. The third graph shows a linear relationship again, but here, the influence of a single outlier is striking. One point far away from the rest has pulled the regression line towards itself. If you were to remove this point, the entire statistical summary would change drastically. The fourth graph is perhaps the most dramatic. All data points except one are aligned vertically. That lone outlier determines the slope of the regression line. Statistically, it's identical to the others, but visually and structurally, it's an entirely different situation. Now, why is this relevant for logistics, engineering, or business analytics? Because in all these fields, we work with aggregated data every day. Whether it's throughput rates, inventory levels, order frequencies, or error rates, we often summarize complex phenomena into single values. And while aggregation simplifies reporting, it also hides details. For example, imagine you're analyzing order lead times across different regions. The average might be 7 days. But does that mean every region has a 7-day lead time? Maybe some regions consistently hit 5 days, while others struggle with 10 days or more. If you only look at the average, you might not even notice this problem. Or think of picking performance in a warehouse. You calculate an average picking rate of 150 units per hour. That sounds fine. But does it reflect the performance of all employees? Maybe one high performer skews the average, while most others work significantly below target. The key takeaway here is that statistical aggregates, mean, variance, correlation, do not tell the whole story. They are useful, but only as a starting point. They should never replace visual data exploration. Let's also briefly talk about the correlation coefficient. Here it's 0.816 in every case. That's considered a strong correlation. But as we've seen, the actual relationships in the datasets are very different. One is linear, one is nonlinear, one is driven by an outlier, and one is entirely dependent on a single data point. Relying on the correlation coefficient alone would be misleading. This example underscores the importance of plotting your data before jumping to conclusions. Always visualize scatter plots, box plots, histograms. These tools reveal patterns, anomalies, and structures that summary statistics might completely obscure. To wrap up this section, let me give you a practical recommendation. Whenever you receive a new dataset, don't just run summary statistics. Always plot the data first. Look for trends, outliers, and patterns. Only after visual inspection should you proceed to aggregation and modeling. Anscombe's quartet is a brilliant reminder of this principle. Even today, 50 years after it was published, it remains a gold standard example of why data visualization matters. Now, let's connect what we've just discussed with the source of this lesson. Francis Anscombe's original paper titled Graphs in Statistical Analysis. This slide shows an excerpt from that paper, which was published in The American Statistician in 1973. Anscombe's point was both simple and profound. In the world of statistics, we tend to overemphasize numbers, formulas, and computational precision, while neglecting the fundamental value of graphical analysis. In the excerpt, Anscombe lists 3 common misconceptions. Numerical calculations are exact, but graphs are rough. For every statistical analysis, there is one correct set of calculations. Doing complex calculations is virtuous, but looking at graphs feels like cheating. Let's unpack these points. The first misconception is about the illusion of precision. Numbers give us a sense of certainty. They're neat, exact, and fit nicely into tables. But the process of reaching those numbers often involves simplifications, assumptions, and approximations. Graphs, on the other hand, can look messy. They reveal variability, anomalies, and outliers. But this so-called roughness is exactly what makes them valuable. They reflect reality more honestly. The second misconception is the idea that there is only one correct way to analyze a dataset. In practice, there are often multiple valid approaches, depending on context, purpose, and assumptions. Graphical analysis offers flexibility. It allows us to explore data from different angles, discover unexpected patterns, and refine our hypotheses. The third misconception is perhaps the most cultural. In many technical fields, there's an implicit belief that complexity equals competence. The more sophisticated your statistical model, the better. But this mindset can be dangerous. If we jump straight into complex calculations without understanding the data's basic structure, we risk making elegant but irrelevant models. Anscombe argued that computers should do both, calculate numbers and draw graphs, and we should pay attention to both outputs. Each offers different insights. Today, this advice is more relevant than ever. With powerful tools like Python, R, Power BI, and Tableau, we can generate sophisticated graphs with minimal effort. There's no excuse for skipping visual analysis. In logistics, for example, visualizing order patterns, demand curves, or inventory fluctuations often reveals operational bottlenecks that KPIs alone fail to show. A simple time series plot might highlight seasonal spikes. A heat map could uncover regional performance gaps. And a scatter plot, like in Anscombe's quartet, might reveal outliers that distort overall statistics. So, to sum up this section, numerical accuracy and graphical exploration are not opposites. They are complementary. Ignoring graphs is not rigor, it's blindness. Let's now look at a more modern and quite entertaining example of why visual data inspection matters. The Datasaurus dozen. This concept was developed by Alberto Cairo and later expanded upon by Matejka and Fitzmaurice in their 2017 paper. The image you see on this slide shows 12 datasets. Each of these datasets has almost identical summary statistics. The mean of X is approximately 54.26. The mean of Y is around 47.83. The standard deviations of X and Y are also nearly identical. The correlation coefficient is close to negative 0.06. In statistical terms, these datasets appear to be the same. If you only looked at the summary statistics, you'd conclude that they behave identically. But when we plot them, we see something remarkable. The data points form entirely different shapes. A dinosaur, a star, a circle, vertical and diagonal lines, and even random clouds of points. This example takes Anscombe's lesson to the next level. It demonstrates that even when we calculate more advanced statistics, means, standard deviations, correlations, we can still be misled by aggregation. In fact, the dataset named Datasaurus, which looks like a dinosaur, was specifically designed to show this. Its summary statistics are identical to the others, but its shape tells a completely different story. So, what's the practical takeaway for logistics engineering and business analytics? Imagine you're analyzing warehouse performance across different sites. You calculate average pick rates, error rates, or inventory turnover. The numbers might be similar across sites. But if you visualize the underlying data through box plots, scatter plots, or heat maps, you might uncover patterns that are invisible in the summary statistics. One site might have high variability due to seasonal peaks. Another might show bimodal distributions, hinting at two distinct operational modes. Yet another might look fine in averages, but suffer from persistent outliers. In simulation modeling, similar dangers exist. You might validate a model by matching average throughput. But does it replicate variability? Does it capture extreme cases? Without visual validation, you might miss critical discrepancies. The Datasaurus dozen teaches us a fundamental truth. Data shape matters. Visual patterns often carry operational meaning, bottlenecks, shifts, structural anomalies that pure numbers obscure. To close this segment, let me emphasize once again. Summary statistics are useful, but they are not enough. Visual exploration is essential for understanding the real behavior of your data.